Okay, you can hear and see me?
We can see, but the screen is cropped to one corner of the screen, like we see.
Oh, wait, like, is it better now?
Record. Yes, much better. Good.
Okay, cool, yes.
Okay, so
okay, okay, thank you. And thank you to the organizers for the opportunity to speak today. Right, so yeah, today I'm going to be talking about second order asymptotics for transforming quantum dichotomies. Obviously, I'll explain what that means in a second. And then I'm briefly going to talk about some applications to quantum thermodynamics. So this is joint work with these collaborators here. Patrick and Joseph are in Switzerland, Marco is in Singapore, and Camille in Poland. Okay. So what is a quantum dichotomy to start with? So quantum dichotomy is just a pair of states, right? Nothing more complicated than that. Okay, that's so far so boring. So now what we're going to do is one of the things that we can do with these pairs of states is we can define something called the Blackwell preorder. This is borrowing, some notation that's used classically. So we can define this preorder, which we denote like this, which is some order on pairs of states. And the way that we define it is we say that this pair of states, preorders this pair of states if there exists a map which sends each state to the corresponding other state, right? So ρ1 to ρ2, sigma1 to sigma2, right? Now, obviously, if we only had a single state here, so I didn't have any sigmas, I mean, this would be trivial, this wouldn't do anything. So we need at least two states for this to be a non-trivial statement. Now, one could extend this, which is actually what this is what we're going to look at mostly in today's talk, which is an approximate version of this, right? Relatively straightforward definition. You now just say, well, instead of exactly mapping, I'm going to say that I get close in some distance measure, right? I mean, you could pick any distance measure you want, infidelity, trace norm, whatever. So now the map has to send ρ1 close to ρ2 and close in the sigmas as well, with potentially different errors here, right? And then, of course, one can extend this even further, which is in fact, this is what we're going to look at today, which is now we say, well, we have some sequence of errors and we have some rates, and we want to look at the asymptotic problem where now we're looking at the trade-offs between these errors and the rates with which we can do this transformation, right? So we're asking, what is the smallest error for which we can do this and what is the largest rate for which we can do this? You can phrase it either way. Okay, so this is just sort of abstractly, mathematically, this is the problem that we're going to be looking at to at least gesture in the direction of some physics. What does this actually relate to? So this is the abstract problem, but this actually relates to several resource theories. Can be sort of phrased in terms of these dichotomies. So the first is, and the one that is thermodynamics, specifically Gibbs preserving thermodynamics, right? So here the free operations are any operations that leave the thermal state, the Gibbs state, invariant, right? And so the way that we can phrase that is we say, well, if both of the sigmas are the thermal state, and I require that the second error is always 0, meaning the thermal state is exactly preserved, and then the first error is whatever, then this exactly captures these so-called Gibbs preserving operations, right? So these transformations, these dichotomies in these parameters reduce to these so-called Gibbs preserving operations. Another is, which is actually a sub-example of this, a subset of this, is the case where you just take the infinite temperature thermal state here, the maximum mixed state. This relates to the resource theory of purity. So again, we're looking at maps that preserve this state with some error, and then we require that they preserve this exactly. So the second error is 0. And then the third is bipartite pure entanglement. Sort of similar thing. It's sort of the exact sort of opposite of this, where you take some product state and with some basis state, doesn't matter which, let's say the 0 state, and again the second error is 0. There is a slight trick here in that this condition is sort of backwards for entanglement, right? So the statement here is that this would be the input and this would be the output. Okay, there's some difficulties to show that you can actually pull these results through, which we looked at in the previous paper, but that's sort of the right basic idea, right? That all three of these resource theories can be phrased in terms of these dichotomies, right? So any results about these dichotomies or transformations of them will tell you about rates in these resource theories. That's the idea. Okay. Okay, some basic notation, which I suppose is probably going to be familiar to most of you. I'm going to use the relative entropy a lot. It's defined like this. I'm also going to use the relative entropy variance, which is maybe less commonly used, which is like a second order version of this quantity, right? If you see this quantity is like the average of this expression here, this is like a variance of it. And then I'm going to use two versions of the Renyi relative entropy, the Petz version, and this sandwich one. I'm also going to use so this is the standard sandwich one. There's something called sandwich one, which is actually going to show up in some situations for alpha less than 0. But okay, the details of that don't matter so much. But this is just the definition that I'm using if you're wondering what's going on with these negative Renyi entropys. Okay. Okay, so I'll just sort of briefly mention what previous results there are in this sort of direction when it comes to these second order asymptotics. So, okay, the first, before we go to second order, is first order. So the first order is relatively simple, which is nice. So here the statement is that if I have some constant error, somewhere between 0 and 1, right, I fix the error to be a constant, and then I look at the rate asymptotically, I approach the ratio of these relative entropys, right, which for notational convenience, I'm going to call C from here on out. In thermodynamics language, these relative entropys with respect to the thermal state can be interpreted as the free energy. So there's a ratio of free energies. And so this is essentially a statement of the second law of thermodynamics, is one way to interpret this. And then for entanglement, you get entanglement entropy. Yeah, okay. So this is the basic idea that you get this, you tend to get this ratio quantity here. An equivalent way of writing it, which it's maybe not straight away obvious that it's equivalent, but if you play around with it, it turns out it is equivalent, is that if I fix my rate to be less than C or greater than C, and I look at the asymptotic error, then it always approaches either 0 or 1, right? In a few slides, I'll show some graphics to sort of suggest why these two things are equivalent. But this is sort of the first order behavior, right? So now we want to go to higher order. So the first, I think, two works on this, there was a paper by Kumagai and Hayashi, and then we had a follow-up paper. So these papers, so this first paper looked at entanglement specifically. So basically it doesn't have these second states here, right? These were just entropies and entropy variances. Okay, in that case, commuting doesn't matter because there's only one state. And here, everything is being done in the infidelity, right? Epsilon is a statement of the infidelity. So, right. So here, basically, what we're saying is we're perturbing this. We're looking at higher order corrections to this statement right here. So here, we're saying that as n grows, we still have this constant asymptotic rate. But here we have, okay, these are all just constants, but we have this 1 on square root n correction here, right? Okay, here is you get this this thing called the Rayleigh normal distribution, the exact expression for this doesn't really matter. But this is the basic idea. You get like a 1 on square root n correction. You can think of it like a central limit theorem type behavior. Right, and so yeah, and then we extended this. The expression that I've written here is the extension to the thermodynamic setting, where you now have these second states. But we required that all of our dichotomies were commuting, right? So rho 1 and sigma 1 commute, rho 2, sigma 2 commute. I know these expressions, right? So that's the main limitation there, and it's an infidelity, which makes the proofs a little bit more annoying, but it's. We also had a second follow-up paper where we looked at the so-called moderate deviation regime. I'll explain exactly what that means in a few slides. But basically here, instead of just doing a constant error, we now are allowing shrinking error, but only sub-exponentially, right? So we have something like e to the minus n to the alpha between 0 and 1, right? So not quite exponential, which is another interesting regime, but anything between exponential and constant we can also do. You get a sort of similar expression, right? You have this constant rate. You have some correction now, which scales like n to this stuff, Okay, the exact expression here doesn't matter, but these two regimes were looked at. Again, commuting, infidelity, the main limitations there. Okay, so the main technical difference today is everything we're going to look at is in trace distance, and it turns out that's going to open up an entirely different proof technique, which is going to be quite nice. One of the major things that you gain is that actually all the results that we're going to show work for non-commuting inputs, right? I make no assumptions about the inputs, but we do have commuting outputs, right? We still require that. We have some of our bounds hold even for general outputs, but for all the tight results, we require commuting outputs. Because of the techniques that we're going to use, they actually sort of quite nicely extend to a whole bunch of different error regimes, right? So I said before that we had, for infidelity, we had results for small deviation, which is this constant error regime. We also could extend it to these so-called moderate regimes where you allow the errors to shrink or grow a little bit. But we can also do the case where the errors are exponentially small, exponentially large, or in fact zero, right? And in some sense, this is sort of all of the different error regimes, right? These all cover all the possible different scalings of the error, which is quite nice. We can also do two-sided error. As I mentioned in the slide about resource theories, in all the resource theories, it only ever makes sense to have the second term have zero error. But actually, mathematically, there's nothing to stop you having an error on the second term. And in fact, we can get some partial results there, even if the applications don't require that. And the main advantage from my perspective is the proofs, I think, are quite a bit more simpler, a lot less involved than was for infidelity, which is one of the reasons we're able to extend all these different regimes, which is quite nice. Okay, so that's a sketch of the basic sort of strengths, the result. So the way that we do this, the main technical tool, is reducing everything to hypothesis testing. Right. So I think this is sort of an obvious other task that you might imagine doing with a quantum dichotomy. So now we have, suppose again, we have a quantum dichotomy, we have a sigma and we have a rho, a rho and a sigma. And we could ask about hypothesis testing between these, right? So now, okay, we have some test, which is meant to be indicating that we have a rho instead of a sigma. We can define the type 1, type 2 error. This is probably familiar to most of you. So now there's some natural trade-off between these type 1 and type 2 errors. I can then define the optimal, this beta expression, which is the optimal type 2 error given a constraint on the type 1 error, right? And then optimized over all possible tests. And this is a sort of sketch of what you expect to see, right? Here I just chose, two random qubit states and just generated this function. And so here, okay, if the type 1 and type 2 error can be really large, that's fine. But as I shrink them, I hit some trade-off, right, between these two things, which is this shape here, and that's essentially what this function is describing, right? I'm describing this curve. So this curve basically describes this optimal trade-off, right? So the really nice thing is not only can we define these two sort of tasks on the level of quantum dichotomies, but they're actually strongly related. So for the case of commuting dichotomy, so essentially classically, there's something called Blackwell's equivalence theorem, which states that I can transform from one dichotomy to another if and only if the beta curve lies above the beta curve of the input. Right, essentially what it's saying. Okay, this backwards direction is quite straightforward to see. Sorry, this forward direction is quite straightforward to see from data processing. The backward direction is not so obvious, but it turns out it's true, which is quite nice. And a quite nice property of the trace norm or total variation distance is that there's actually an approximate version as well. So here the statement is that I have this approximate Blackwell order only if I have a similar sort of expression, but for shifted betas, right? And so what this sort of looks like is now I have the beta curve of my input. Let's say I have the beta curve of my output. So in this case, the beta curve of the output is not above the input. But if I shift it, so this corresponds to a horizontal shift, this corresponds to a vertical shift. If I now shift it, now it is, right? And so the statement would be for these parameters, then I do have this approximate ordering. And so you can think of these errors as basically saying, how much do I have to shift this curve, either horizontally or vertically to get it above, right? Now, the really nice thing about this is these betas asymptotically have been studied to death, right? In all the various regimes, I mean, that's essentially how our result is going to work, right? We're just going to apply all the asymptotic statements about these betas and all these various regimes and pull this across to tell us about the rates over here, right? That's the basic idea. There's some technicalities in getting that to work to do with this for all and uniformity and okay, but that's the basic idea. Okay. Now, everything I said here is for commuting dichotomies. So how do we do non-commuting, right? That's one of the main features that I mentioned is that we can deal with non-commuting inputs. So right, as I state here, it's known actually that not only does the proof break, but in fact it's known that the beta ordering in this way does not actually imply this Blackwell ordering, right? Even the non-approximate version of this is known to not generally be, this is not enough, right? So what we're going to do is we're going to define another sufficient condition. Now for single shot, it may not be good enough, but actually in these asymptotic regimes, we're actually going to see that this is good enough to get tight results in most of the error regimes, which is quite nice. So here we're going to define this P sigma is the pinch of sigma with respect, the pinch of rho with respect to sigma. And the key thing now is that if I pinch rho, then this commutes with sigma, right? And so now I'm going to define, I'm going to look at the hypothesis test between the pinched rho and sigma, right? So I'm going to define this pinched type 2 error to just be the type 2 error where I pinched the first state. It's now, not symmetric, but that's okay. And so I'm gonna pinch the first states, and then for the second states, I'm just going to assume that they commute, right? In all of our results, we required that they were commuting. So if this is true, then I take, if I have, so instead of this quantity up here, now if I have the pinched type 2 error here, and I have the same expression from before, well, now this commutes because of pinching, this commutes by assumption. So that implies this Blackwell ordering on the pinched guy. But actually you can show that, well, what does this expression tell us? Well, it tells us there's a map that sends the pinched guy to sigma 2 and, sorry, to rho 2 and sigma 1 to sigma 2 approximately. Well, okay, I can just, the map that I get from this composed with the pinch, therefore that also implies that I just have this Blackwell ordering directly, right? That there's this sort of data processing, if you like, inequality of Blackwell ordering, right? If I can do it on something that's already been acted on, then I can do it on the raw state itself, right? So this gives us a sufficient condition. So in other words, we have the Blackwell ordering, the thing we care about, that implies this beta ordering, and it's implied by a slightly modified version where you pinch, right? But similar sort of expression. Now in the single shot, these two expressions could be very far apart, right? This would be a potentially crude bound, but it turns out asymptotically, this pinched beta is actually going to have very similar asymptotics to this. In fact, it's going to have the same asymptotics to second order in all but one error regime, which is going to allow us to get tight bounds on the rates here. Okay, so I've sort of mentioned small, moderate, and large deviation as sort of regimes of these second order asymptotics. Just a quick sketch. You aren't familiar with this sort of notation. So here we want to look at the trade-off between rate and error as we increase the number of copies, right? So intuitively, low rate, we have some complicated mess, and then as we increase the rate, as we increase the number of copies, I should say, what we sort of know from the first order is that this should sort of naturally approach a step, This is obviously this is a sketch, but this is the idea that we approach this step behavior at the asymptotic rate here, right? And so yeah, so the first order statement is just that we approach the step. All the second order statements are, okay, how quickly do we approach this, right? Well, there's multiple ways you could quantify that convergence. The first, and this is the regime that is often referred to as second order, but I think in some sense you can think of all three of these as second order, is the so-called small deviation regime. Here we fix the error, we look at everything horizontally, and we look at how quickly the rate approaches the asymptotic rate, right? So we're looking at how quickly these curves are moving horizontally. So here we have constant error, and we expect a 1 on square root n behavior. Another regime is this large deviation regime. Here we fix the rate to be something either below or above the asymptotic rate, and we look at how quickly the error approaches either 0 or 1. And we generally expect it to be exponential. Okay, and then there's this sort of weird intermediate regime called moderate, which is somewhere in between, right? We're approaching the asymptotic rate, but we're doing it, slower than 1 on square root n, and we're approaching 0 error or error 1. And okay, this is just sort of a gap that's left between these two regimes. I think the large and small are the more sort of easy to motivate regimes, more natural regimes, but yeah, we can actually do all three of these, which is quite nice. And as I said, for infidelity, only these two regimes on the left have been looked at. Large has not been looked at. Okay. Okay, so now I'll get into the results. Okay, the exact details of these expressions don't matter so much, but basically what we find in the small deviation regime is a very similar to expression to what was previously found for. So here we have the asymptotic rate. We have this correction involving these entropy variances, again, a 1 on square root n behavior. But here, this quantile function we get, as with infidelity, we don't have a Gaussian term, as you might expect. We get some slightly more complicated distribution here, which is related to the Gaussian, but is not the Gaussian. But here we actually get a different distribution. So in the previous result by Kumagai and Hayashi, they got something called the Rayleigh normal distribution, which sort of interpolates between the Rayleigh distribution and the normal distribution. Here we get something that we call the sesquinormal distribution, which I've sort of given an expression of here, which actually interpolates between the normal and the half normal, which is slightly interesting. We also have a way of writing an expression for what you get here explicitly in terms of the distance measure you use, which actually reduces to the two existing results, which is quite nice. But, yeah. Okay, we can also do the moderate deviation results. These are actually identical to the infidelity results, it turns out. Okay, the details of these don't so much matter, but now we can do that in Tracenorm, which is quite nice. Okay, and then we approach the wall of text. Okay, so then we can also do large deviation. Here, the results are not so straightforward, but I present them nonetheless. So in the high error case, we have an error exponentially close to 1. Okay, this expression isn't too bad. We get some, so now we get the Renyi entropes are showing up, sandwiched and pets, and we get some optimization of these expressions. In the low error case, things are a little bit more complicated. We actually, first of all, here we have a two-sided bound. We have the asymptotic rate. Here we have two bounds, but they're actually not generally the same, right? So we have a bound on the lim sup and lim inf, but these for non-commuting states are generally different. And again, you get these sort of expressions involving Renyi entropies, now optimized over a bunch of different regimes, and then you take an inf. Okay, but the very similar sort of expression morally to this higher expression. Okay, so you get something involving Renyi entropes is sort of the idea. And obviously, if everything is commuting, these tildes don't matter. Sandwich equals pets. Everything collapses down, and we get type bounds in this regime as well. Okay, I have a few minutes, so I'll just briefly sort of mention one of the really nice things from an application perspective that you get, of course, now is that I'm allowed to have coherent inputs, right? All the previous results were only ever looking at commuting input and output. So if we wanted to look at, applying this to thermodynamics, that's pretty limited. We could only look at so-called energy incoherent states, which commute with the thermal state. Now, for our results, that's still true of the output, but the input is allowed to be coherent. The input is allowed to be general. So now we can ask questions of, well, what if we look at some states and we vary them by their coherence? Does this actually affect things? So here, okay, this is the block sphere. I think the red dot here, the red dot here is the thermal state. The blue dot here is the target state. And then we want to look at these row ones, which are anywhere on this white dotted line. Right, we're varying it by coherence, all the same energy but different coherence, and we could ask the question: okay, if I want to run them at the asymptotic rate, what is the error associated with that transformation? And so what we find is that there are these sharp dips. We had a previous paper looking at this phenomena. We called it resonance, but in this coherent case, you actually can get quite complicated behavior where you have multiple resonances. Which is quite nice. So as I vary along this line, I'm getting that my error is dropping really dramatically and then picking back up and dropping down and so forth. So these coherences can vary the errors quite, which is quite interesting. Okay, so I'll just come to a summary slide. So yeah, so we showed that we can do second order asymptotics for these quantum dichotomies. And rather nicely, we can do it in all the various error regimes. I think I didn't mention zero error, but we can also do that. So in some sense, we can do every single error regime, which is quite nice, at least to second order. We have tight results for general inputs in all but one regime, and then obviously if everything commutes, everything's tight, and then we have one-sided bounds for general input-output. And one thing that I hinted to, but obviously we haven't looked at in much detail, is this obviously opens the door to studying the role of coherence in things like resource theory in these asymptotic settings, where up until now everything has had to be commuting. Yeah, so I'll leave it there. Thanks.
Okay, thank you, Christopher, for this very nice talk. Are there any questions?
Okay, I have a question. So could you please go through the page of the main results?
Which ones? These ones or?
Yeah, okay. So does this, so you mentioned that the results, if I understand correctly, it was for general rho 1 sigma 1, but need rho 2 and sigma 2 to be commute, right?
Yes, that's correct.
So how about the next page about the large deviation results?
Yep.
Do you still need rho 2 and sigma 2 to be commute? So
yeah, okay. So the actually in both of these, so yeah, okay. That, I mean, you might have wondered why I'm, for example, putting a tilde on this expression here. If these are commuting, why does this matter? So in all of these results, so let's come to these small deviation results, for example. The upper bounds that I've written here hold for general input, output, everything, right? They just hold from data processing, right? So if you just look at the upper bound here, that's fully general. The achievability, the lower bound, for that we require the second pair is commuting, right? So so here when I write this sandwiched expression here, I've written that because, well, if these are general, then actually this upper bound here, that does hold still for general states.
Okay.
The law bound that requires the outputs to be commuting. Yes.
Okay, I see. So also for high error case, I mean, the result in the left side, you also need rho to sigma to be commutative.
For achievability, yes. For optimality, no. Right. So the upper bound,
Okay,
and here we have an upper bound and a lower bound, right? Yeah.
Okay.
The upper bound is general.
Okay,
Yes.
I understand that. Yeah, it
Yes.
looks very interesting. Okay, thank you for
Yes,
the answer.
I mean, it is to give you the slightly the details of, basically it comes down to this expression, right? Like obviously this leg of it, I don't need any commuting assumptions, right? This is where we get optimality, and then here, okay, here we start using commuting, right? This is where we get achievability, right? So this is why
interesting.
yeah, that's the basic idea. Yeah.
Okay, thank you.
Thank you.
Okay, so let's thank Christopher again.
Thanks.
And now our next